Hello, so today I'm going to talk about a new mathematical model that we created called LTAR, where we want to be able to take data dependent on time to predict samples that are two-dimensional. And so overall, this is an extension of previous autoregressive techniques where they try to predict a time series where the samples are scalars or vectors. And so here we can see that we have a bunch of matrices dependent on time, and we want to be able to forecast those. And so to do that, we've created a model called LTAR. What LTAR stands for is transform-based tensor autoregression, where basically we apply some sort of transform, and then we do a autoregression model as shown here. And so this will allow us to apply this to a variety of domains, such as being able to predict future frames within a video, or predicting how a network will change, like a social media network, and how maybe friendships on that social media network would change. And even landscape data. Say if you have a landscape with a bunch of temperature data and you want to predict how hot it will be in the future. And so here's an overview of our technique. And so overall, this is a divide and conquer type of method, where basically we take our larger problem and we break into multiple subproblems. And so first we apply a transform across a dimension, giving us statistical independence. And then what we can do is that we can regroup those vectors in the other dimension into smaller data sets. And so now we end up with a bunch of smaller data sets where the samples are vectors, and we can use those previous techniques mentioned previously to perform a vector autoregression to get our predicted vectors. And then we want to go back to our original matrix structure. We group those predicted vectors into its matrix and do an inverse transform. And so when we look at the accuracy compared to other type of methods such as MLDS and LMLDS, we achieve greater accuracy with a similar computational complexity. One data set we looked at was a data set of sea surface temperatures, and we perform far greater accuracy because our percent error is way lower. We also try to use it to pick up patterns. For example, we use the MNIST data set, which is a data set just of a bunch of handwritten digits, to create a recurring sequence of 0 through 9. And then we predicted the next 10 values, and sure enough, it is able to predict or is able to pick up the sequence. Overall, this will help us predict two-dimensional data in the future. Thank you for listening about LTAR.